Okay, so good afternoon, everybody, and thank you for being here. Today we will speak about nuclear forensic with the help of Professor Clemens Walther. First of all, I would like to thank Professor Walther for accepting our invitation. Few information about the professor. Clemens Walther studied physics and nuclear chemistry at Mainz University and the University of Seattle. From 1999 to 2011, he was employed at the Karlsruhe Institute of Technology, in particular in the Institute for Nuclear Waste Disposal, serving as group leader in the actinide nanoparticle analysis group and as the deputy department head of the actinide speciation group. He is currently full professor and head of the Institute of Radioecology and Radiation Protection at the Leibniz University in Hannover, and served as a chair of the mass spectrometry section of the German Physical Society. I think that was able to combine all his experience on actinides and mass spectrometry to contribute to this field of the nuclear forensic. So now I would like to leave the floor to Professor Clemens Walther for his presentation. Thank you.
Yeah, thank you very much for the nice introduction. And you mentioned it in the title, so I'm going to give a talk on nuclear forensics. And since you asked me to make it a bit for a broader audience, I'll start with what it is all about. So just imagine you have some kind of finding like this. And then, of course, you'll ask, what is this? Where does it come from? And does it pose maybe any harm? So the usually W question, what, who, where, when, how, why, should be answered here in this case. And so to say, the nuclear forensics is the subdiscipline of classical forensics. So you all see these CSI movies and you know what a crime scene looks like. So in some cases, nuclear forensics is that way if you have findings of very dangerous material in large amounts, but sometimes it's quite the opposite, that you have only traces of material available that you could hardly see and detect, but still want to know where does it come from, who did it release, why is it there, who fabricated it, where and what. So what you typically want to answer are the question on the age of the material, what kind of isotopes are there, so the possible origins, so what kind of trace elements are in here, and traditional signatures. So the parameters can be detected, for instance, by radiometric material, because it's radioactive material. And on top of it, you use a set of another techniques, so typical material sciences, so how does it look like, how does it look like on the micro scale, or also classical forensics. If you have any idea who put it there, then you can get some information on the person, and that is a bit like in the police department. So the workflow, if you start with some material you just found somewhere, you do a sampling, then you categorize the material, and then you build a hypothesis. Where could it build from? Because you never can start from the very beginning and do all kinds of investigation. That simply takes too long. So you start with the hypothesis, and so probably you have some hints where it might come from, and something also very important, you need a knowledge database. So if you do the measurements and find the properties of the material, you have to compare it to something, to some known data, just to correlate with these data. And there's a kind of a database for nuclear forensics, the I2WG. And since 1995, there's an international working group for nuclear smuggling, and that came to life more or less after the fall of the Soviet Union, when there was illicit trafficking of nuclear material starting in a way that was not known to that date. So coming back to our sampling, you do analysis, and on the basis of this knowledge database, you get some information or get some hints which kind of properties should be interesting. So you do some characterization with traditional chemical and physical analysis methods. Then you have to do an interpretation. Most of the time you exclude where it not comes from, and then you can, with more or less confidence, find out what was the origin. So first of all, you need to know, is it radioactive at all? So if it's not radioactive, then it's not nuclear forensics. So if it is a high level radioactivity, you can detect it with a Geiger-Müller counter like shown here. So that is just a piece of paper and you have some dirt on it, and some of the dirt might contain particles, and these particles in turn might contain radionuclides. If that is the case and you're lucky, then it is a gamma emitting material, and gamma emitters are easily measured with high purity germanium counters, and you can not only get the information that there's gamma radiation in there, but also what kind of gamma radiation. That gives you some hint on the isotopes present in the material. So also you start with some visual inspection, and you start with what is most easily available, an optical microscope, and here you find a tiny little particle. We know where it comes from, and we know that there's radioactive material in there, but in case you don't, you can just start and get some characterization on the scale of a few micrometers, because as you know, you cannot go down much smaller with the resolution of an optical microscope. What you can do with an electron microscope, and here you see some particles that are radioactive, and these particles are characterized well on the microscale, and you can see at first glance that they differ very much in the kind of structure, and also the kind of structure you find is characteristic for the material. The next thing you might be interested in is the elemental composition. So is there uranium in? Is there plutonium in? Is there some fission products in? Of course, you might be able to tell from gamma, but there might be additional elements not emitting gamma specs. And then you can do X-ray fluorescence if these elements are a major component of that sample you have. So X-ray fluorescence, you have an incident X-ray beam, and you ionize, so you get some electrons emitted from the shell, and that you get electrons from the outer layers filling up that gap, and by that way emitting characteristic X-ray fluorescence. And this X-ray fluorescence can be the basis of a mapping. And here in this example, you see that there's some uranium in here, and that there's also some zirconium in here, but they're not correlated when it comes to the location. Very good. Another option, what is done very frequently, is mass spectrometry. Here you see just a generic mass spectrum, and that mass spectrum can be obtained by different methods. So typically you have low sample volumes and have a very low number of atoms to be detected. Sometimes you even have to suppress against neighboring masses or a high excess of other isotopes. And two out of many methods you could use are the AMS, you see here, or you can use SIMS, secondary ion mass spectrometry, and the secondary ion mass spectrometry, a little different instrument from what you see here, will play a role in the second part of this talk. Then if you're interested in the structure of the sample, you can use XRD, X-ray diffraction. So this is an example of a micro XRD. And here I just show you a sketch of how X-ray diffraction, Bragg scattering and partition works. You get an X-ray beam, have the diffraction pattern measured here, and that gives you some information on the distance between atomic layers. So you can get lattice distances, and if you do it a bit more advanced, you can do Laurel scattering and get also information on angles and of different layers and on the inverse lattice of the solid. So it would lead too far here, but even in very small samples, microns, you can get real good crystal information on your sample. Of course, that is also used in safeguards. If you're going to nuclear installations and want to know, will they use only enrichments in a certain scale, let's say up to 5%, that is allowed, or 7.5 or up to 19.9% that are typical values, or are they trying to use weapons grade material? But that is a different story. That is not part of my talk, but of course that is also part of nuclear forensics. IAEA is doing that a lot. So in our case, I will lead you through a simple case study. Just imagine you have some piece of dirt here, and somebody told you that might be radioactive, and then you're trying to find your way through this piece of dirt. So where's the origin? And that might be of different origin. So if you just know there is soil and that might be radioactive, that might be, if somebody tells you it is from the Ukraine, be from the fallout of the 60s. You see that here, because there was global distribution of radionuclides, and not only in Ukraine, everywhere you have certain background of cesium-137 or also plutonium in the soil. If you dig up your garden soil, you will be surprised how much radionuclides there are in here. Or it might be, to go to the very right, just some remnants from the 1986 accident in the Chernobyl nuclear power plant. That was also distributed over wide areas in the Ukraine. Or might it be of recent origin? You all heard of the Zaporizhzhia nuclear power plant. It's just in the news again right now. And if there should happen to be any release, could you tell whether it's a new release from here and just nobody admitted that it was released, or is it some old from the very right or from the very left? And I will show you how we can distinguish that by doing nuclear forensics, and in special we will measure the isotope signatures there. So some basics. If you look at the nuclear fission, then you have a chain reaction. You start with a single neutron here, hit a uranium nucleus, then you will fission that nucleus and you will create additional neutrons. These neutrons will head a second generation of uranium nuclei, cause some more fission and so on, and then you have an avalanche and a self-containing nuclear reaction. So if you look a bit into detail of the products, you start with the fissile uranium-235 nucleus here, then you produce two kinds of nuclei here, a little bit smaller one and a little bit bigger one, and 2 to 3 additional neutrons you need to sustain the chain reaction. And if you ask what the products are and look into the periodic system, bad news. You will produce a lot of different elements, and each of these elements contains quite a number of isotopes. And you have these fission products that are considerably smaller than uranium, and you have the uranium itself and some so-called breeding products, that is the minor actinides, plutonium, americium, curium. And these are present very characteristic of the source in nuclear material. So looking at the chart of the nuclides, you start with just the uranium and the oxygen. So most of the fuel is uranium dioxide. And then you go to produce the fission products and you produce the neutron activation products like the actinides here. And in addition, you have some nuclides of the uranium decay chain, and you have some very light fragments. And all these products might be in your sample, and then the question is, which of them can be used to trace back the material, which of them are very characteristic of the source and of the age of the material. So let's look at the different reactor types in question. So if you look at the most frequently used reactors in the world, that are the light water reactors, that is the pressure water reactor here to the left, and the boiling water reactor here to the right. And in that lower section, you see the RBMK reactor, that is the reactor of the Chernobyl type. And each of these reactor types uses uranium, enriched uranium as a source, but the isotopes produced during operation of these reactors are quite different. So something more, if you start with uranium pellets of like 10 grams, then you fill in a Western type reactor 300 of them in a fuel rod that is 4 meters long, and the energy of one of these pellets is like 1 ton of coal. I said it is approximately 1 ton of coal because the amount of energy you produce depends on the burn-up. Basically, that means how long can you use that uranium-235 in your reactor. That depends on the kind of reactor you use, on the kind of moderation you use, on the initial enrichment, and of many factors. And that is also, of course, a pattern of the reactor tube, a pattern of the source of your potential material. If you can afterwards tell what kind of burn-up was used for this material, you just find. And the higher the burn-up, the longer the fuel remains in the reactor, the higher is also the production of the plutonium-239, because that is an activation product. And if you start with the uranium-238 and start absorbing neutrons, then you produce the uranium-238, have 2 beta decays, and go to the plutonium-239. So you have many, many isotopes, and if we look a bit more detailed into this region here, the high region with uranium, then you start from the uranium-238, absorb a neutron, go to the plutonium-239, as I just described. And then if you have extra neutrons, you can absorb one more, end up with the plutonium-240, end up another one with the plutonium-241. Then you can either absorb another neutron, then you're at plutonium-242, or with a certain probability you have beta decay of the plutonium-241 to the americium-241. And that again can absorb a neutron, or you can also go different ways to the americium-242. So all of these will be important for the present study. In addition, the 235 uranium can either undergo fission, or it can absorb a neutron and be 236 uranium afterwards. Another neutron goes to uranium-237, then neptunium, and in the end plutonium-238. So these are the major and important plutonium isotopes you have to detect, and also these americium isotopes along with the uranium isotopes to identify the source of nuclear material. If you suspect it originates from a nuclear reactor. Of course, there are different sources, but if you suspect, as in our case, it might originate either from a nuclear explosion or from a reactor, then that is the way to go. So how can these plutonium isotopes vary for different sources? So this is the ratio of plutonium-240 divided by the number of plutonium-239 atoms. And if you look at weapons-grade plutonium, that number is rather low. If you look at the average weapons fallout, so what was done in the 60s and distributed over the northern hemisphere quite homogeneously, then you end up with a plutonium-240-239 ratio of around about 0.18. So if you find something like this, it is most likely not from a nuclear reactor, but from the fallout. The power reactors span a huge range, but that range is considerably higher than 0.18. And if you look at the Chernobyl, the RBMK type reactor, then that was more or less between 0.4 and 0.5. So that is rather characteristic. And if you look at different reactor types, like a boiling water, a pressure, and advanced gas-cooled reactor, then you have different kind of plutonium-240-239 ratio. So that at least is one kind of fingerprint you might use. So measurement of the isotope signatures is probably one of the ways to identify the source. And how does it look in reality? So the motivation is just to look at the source. And here you see our group, one of the Chernobyl reactor that was sampling in Fukushima here, and that might be what we end up with the very small particles, like a few microns in diameter, and we want to get some identification of the radionuclides. We want to do that by imaging, not only detection, but we want to have a spatial image, because even on this scale, it might be important to look at the structure and distribution. We want to do everything at the very low level, at the ultra trace level, and we want to get information on the isotope ratios. And in many cases, there are no commercially machines available. So for this one example here, I present you how we handle this. So a typical workhorse for nuclear forensics is the secondary ion mass spectrometry, because you have a low sample consumption, and in this case of a so-called static secondary ion mass spectrometry, you can also measure insulating samples. That is interesting if you do environmental monitoring and find your samples in nature that they typically are not conducting, and you end up with a rather good spatial resolution. So the idea is that you have some primary ions, that ions hit a target. Hitting the target gives rise to emission of neutral atoms and ions, and the ions are extracted into a time-of-flight mass spectrometer. Run here, you will see an animation just later on, and then they are selected by mass over charge ratio, and you get information on the mass of your samples. Since you can also do imaging, you just scan your primary ion over the probe, and then you can get information on different elements, and in this case here, that was not nuclear forensics, that was just natural minerals from Afghanistan, and there we had minerals where uranium and thorium were in, but it was natural occurrence because we were asked, was it depleted uranium ammunition, and we came to the conclusion, no, it was not. It was just a natural mineral containing a lot of uranium. So also with the secondary ion mass spectrometry, you have some downsides, and the downside here is the poor suppression of isobars. You have a low selectivity, and when I imagine here the sputter process, 99% of what you sputter off is neutral atoms, and the neutral atoms cannot be extracted into the mass spectrometer here, only the ions can, so you throw away 99% of what you produced and detect only 1%. So still, you can get nice information here. You see that particle again, you see the uranium isotopes. This is uranium-238. This is uranium-235. You can tell that you have a uranium ratio that is slightly different from the natural uranium, so that was enriched. Then you see uranium-236 that is not present in natural uranium, so you know it spent quite a while in the reactor. And these red lines here, these are probably not uranium, so you suspect that might be plutonium, also a sign that the sample came out of a nuclear reactor. But it might be plutonium, it might also be just an artifact of your mass spectrometry measurements. That is uranium hydride, and uranium-238 plus mass 1 of the hydrogen gives you also 239, and that is hard to discriminate. And at the 241 mass, similar problem occurs because there's a americium-241 isotope and a plutonium-241 isotope, and that might not be discriminated. And again, at 238, you have the prominent uranium peak, but there might be just a minute amount of plutonium-238 also in this peak, and that needs to be known for some purposes. So the method we do that is with the so-called resonant laser SNMS. You see here part of the table of the nuclides, and if you do the mass spectrometry, you can single out just one isobar. So all of these isotopes have the mass 238. And if you now apply a selective ionization process, then you can single out just one element, and that just gives you the plutonium-238, which satisfies the 238 isobar condition and being a plutonium element. And how do you do that? If you picture just the neutral atoms, you fire at these atoms with the laser, and you do it in a resonant 3-step excitation scheme. So here is the atom, and then you excite an electron to 1, 2, 3 steps, and then it is excited to exceeding the ionization energy, and then you produce plutonium-238 ions. So it is a selective ionization of just one element, and that gives you a very high element selectivity, and together with the mass spectrometry, it gives you an isotope selectivity. We just said that we fired the ions here to the surface. You see them coming here. Then you produce ions, secondary ions, by firing the laser. And after you successfully produce these ions, they're flying to the TOF analyzer, and you can get a mass spectrum here. So if you blow up that region, that is the laser coming in with a 3-step laser, giving you these nice colorful schemes here. And then you produce your ions that you can detect in your mass analyzer. And how good this scheme is, you can see at this view graph here. So that is not plutonium, that is technetium. And if you have an environmental sample, then you have a high organic background, because at every mass you see at least one peep, sometimes several. And this is the technetium oxide, and technetium dioxide. So if somebody tells you, though, that should be technetium, I'm quite a bit of skeptical, then you switch on the lasers and all the rest of the background is just gone, and the only thing remaining here is your technetium-99. And that is pretty much convincing that you have a nice background suppression and a good selectivity when you combine the SIMS and combine the lasers, and we call it secondary neutral mass spectrometry, that is SNMS. So of course it's a bit more than this, because the left picture shows you how you get your samples in nature, and the right is the instruments you want to put it in. And it is not a good idea just to take a shovel of dirt and put it in there. That might not be what you want to measure. So what we really do is just finding some samples, and we go to regions where we expect radioactive samples to be. Then if you just imagine that shovel of dirt I showed here in the beginning, then we do some sieving, have the grain size reduced step by step, and then we look at very heavy particles, because we know if you look at particles containing uranium, they have a high density, and we do a special kind of flotation, but this is not water here. This is polytungstate that has a specific density of 3 grams per cubic centimeter. So everything with a density lower than 3 grams, for instance, aluminum phases, silicate phases that float on top of that liquid, and we are only interested in what is even heavier and falls down. Then we put that particles in the electron microscope, have it in the backscattered electron mode, and in the backscattered electron mode, everything that has a very high Z, a high atomic order, shows up bright. So you can see the particle here. And then we want to position that particle onto a very tiny tungsten needle and glue it with a special glue that hardens under the electron beam. And here you can see the tungsten needle and the particle attached to it. That is a macroscopic view. And then imagine we have a tiny piece of nuclear material on here, and then we can do additional experiments like gamma spectroscopy or EDX or mass spectrometry, everything that I showed to you in the beginning that we do. So here is an animation. You see that particle under the electron microscope, and you have the tungsten needle. The tungsten needle attaches to the particle. The particle is on the substrate right now, and as soon as you are in a good position, you touch that particle, then you apply an electron beam to harden the glue, and when that was successful, you can single out that particle and have it mounted on your tungsten tip for further investigations. So that tungsten tip gives you also a good background suppression, because if you compare this one, this is an unprepared environmental sample in our mass spectrometry picture. You can see the uranium, but you can see all kind of additional peaks. And if you look at the same picture just done when the particle is mounted on the needle, then you see that most of the background is gone, and you see the uranium isotopes remaining. And here you have either uranium hydride or you have plutonium. You cannot decide at this time. You can decide later. So coming back to our case study, we just assume we singled out a particle from that dirt, and now we're going to investigate this particle. And what we first do is, since it is in the electron microscope anyway, we do an EDX. And the EDX gives you first information on the element. So of course it contains uranium and it contains oxygen, so that gives you a hint that it indeed is nuclear fuel. We have some aluminum and silicon on it, but that might be due to the substrate here. Then you switch on the laser and you tune the lasers to the plutonium resonance. So only the plutonium is ionized here. And that gives you a number of peaks, the 238, the 239, 240, 241, 242. And also the 238 is a bit critical, as I told you, because we know now that the particle is composed mainly of uranium-238. And there is only a minute amount of plutonium. And here, with the black peaks, we detuned the first laser, so this blue one here, by 150 gigahertz, so that it's no longer in resonance, so that it now hits just below this resonance state. And that means that the uranium is still ionized a bit non-resonantly, but the plutonium is not. And that gives you, so to say, the background contribution, and everything in excess here, that is the true plutonium-238 signal. And that gives you a suppression of the uranium-238 that would have been right to the top here, just on the top of the slide would be the uranium peak, and it is suppressed by 5 orders of magnitude to that very selective excitation scheme. And just to know that we are on the safe side here, in this case we knew what the sample should be, just compare what we find out with the SNMS and what was done by a macroscopic amount of sample. That was done on a sample amount of grams, and we did it on a particle just a few microns in diameter, and that agrees pretty nicely, even for that very hard to measure plutonium-238. If we suppress the plutonium against uranium, the next thing we did was suppressing the plutonium against the americium. We have the 241 peak, and again, we have on the same mass plutonium and americium and need to detect that. But here I want to focus your attention on the 242 peak, because in the americium you produce as major isotopes plutonium-241. That is also additionally produced by the decay of plutonium-241. And you produce plutonium-243 from the uranium-238 and a lot of neutron absorption. But there's also a tiny peak of americium-242, and that is the long-lived americium-242M. And we were quite proud to firstly detect that in a single hot particle with this technique. And that is amazing what you can do with this technique, because I told you that it's hardly invasive, meaning the particle mass is only 16 nanogram and the particle content of the americium is circa 3 femtogram, and the SNMS does not use up the particle. So even after hours or days of measurements, the particle is still there. So you consume only like 10 attogram of the material to get this kind of spectra and unequivocally detect the 242M. And now we have the information on the uranium isotopes, we have the information on the plutonium isotopes, on the americium isotopes, and that can also done for the fission products like strontium. So if we throw everything together, we just build so-called 4 isotope plots. And these 4 isotope plots give you here the ratio of plutonium-240 to 39 on one hand. So just remember, so the weapons plutonium was at the very low side and the reactor plutonium here. And in the same plot, we also scale the plutonium-241 to 239. And the green dots are what we did from that handful of dirt. So we found particles here. And we know from literature, from the database, how that should look like for a pressurized water reactor. So that is the Zaporizhzhia type, the gray symbols here. And what it looks like from the Chernobyl type reactor, where we have the blue shaded here. And even that we use only that minute amount of particle mass, we can show very convincingly that it was from this reactor type. And here's another 4 isotope plots, 235, 238. We call that burn up, because you start with a certain amount of uranium-235 in the fuel, and that is consumed by nuclear fission, and the longer it spends in the reactor, the more energy you produce, the lower the amount of uranium-235. And at the same time, you see the buildup of uranium-236. And if you compare these 2 isotope fractions, you can tell what kind of fuel was used in the reactor. So from the left graph, we already know it is RBMK fuel. And from using this isotope ratio, we can even tell, was it 1.8% enriched in the beginning, or was it 2% enriched in the beginning? This red line here is the 1.8 enriched, and this line here with the blue symbols is the 2.0 point enriched, and we know that all our data points are 2.0 or even a bit higher. So you can not only tell the origin, we can also tell kind of a history of the particle, what it experienced. And this dot here belongs to that particle I introduced in the beginning. And the particle in our nomenclature has the name Bob. So when we bring it all together, we can exclude the Western kind of reactors. So it originates from the RBMK reactor. We can tell the composition. I didn't show everything in detail, but we can tell from the EDX and other methods that it contains the uranium dioxide zirconium mixed phase in that particle. And we can also tell what kind of fuel was used, uranium oxide fuel with an original 2% enrichment, and we could tell how long was it used in the reactor, so a burn-up of 10 microrad day per kilogram. And just remember that all this information was obtained from a few picogram of material, so really tiny, tiny amounts of material and consumed. That was less than a femtogram, though that particle is available for many other investigations, even after you did that nuclear forensics on it. So the last question is it a rare event that you find some nuclear material and don't know where it comes from? Probably you heard that from radio and TV that in Australia a source was lost. So that was cesium-137 source, and in that case it was kind of inverse. You knew that a source was there, and then it was lost, and then you only had the way to detect that in 1,600 kilometers road, just to go there and drive there and look for gamma radiation and find that source. In the end it was found. But then there are different kinds of findings where you have some material and don't know where it comes from. And if you look at the IAEA website, you find that in the last 30 years, you had 4,000 confirmed incidents. So it is not really rare. And 40% involved nuclear material, and 50% occurred during transport, authorized transport. And so you started with transporting the material in one day, and in the other day it was just no longer there. And in other cases you found something and don't know where it comes from. And there's also thefts. So there's also some criminal energy that people are trying to get their hands on nuclear material just for instance for terrorism. So we distinguish that is trafficking with no malicious intent. For God's sake, that is the highest number of incidents. And until the early 2000s, you have like 100 or even 150 cases per year of this trafficking. You have finding of nuclear materials and don't know where it comes from. So the numbers of malicious use, where you have terrorist intention or others for this nuclear materials, are decreasing in the last years, but it reached a maximum of 15 to 20 cases a year, so that number is not so low. And so that gives you a motivation why we should do research like this. Here you see all kinds of nuclear materials with their special names. Here you did part of my institute doing this kind of research, and you see all the people giving money to this. So thank you for your attention. And what was missing here is of course the CINCH symbol and the CINCH number that was the thing that was in the new version, but this is the old version. Oh, beg your pardon, that exactly this is now missing in this CINCH webinar. So thanks for your attention, and of course, if you have any question, I am very pleased to answer them.
Thank you, Clemens. It was very interesting to listen you. You give us a lot of data, but also details, and explain very well the process you follow to start from the material and to give to this material an origin and end in history. Okay, now we have time for some questions or comments. So I would like to invite the audience to open the microphone or to write in the chat for asking questions to Professor Walther.
Concerning the series of investigation about mass spectrometry and so on, I have seen that generally you are able to measure the isotope ratio, and this is important for concluding some investigation. But I am quite confident with mass spectrometry, ICP-MS, quadrupole and triquadrupole. And for us, the matrix must be always dissolved in a liquid, and so we can do easily a calibration. Is it difficult to calibrate the other instrument of mass spectrometry for quantitative analysis of single isotope or not?
Yes, indeed, it is difficult. And we spent quite a bit of energy to produce reference particles, and still are not completely there. There's a whole European project right now just focusing on the way of how to get certified reference materials, because you need to get that isotope ratios from typically a liquid into a solid phase by co-precipitation or something, or scavenging. And then also the SNMS, like all secondary ion mass spectrometry methods, are dependent on the matrix. So if you have it as an oxide or as a pure mat or different ways of solid states, the ionization efficiency might be different. So that is really a good point and a very necessary point to have good reference materials. In the end, that method is very strong for isotope ratios. That method is not too good for absolute amounts. So if we're interested in the absolute number of atoms of an element, so we have to combine this technique with, for instance, EDX, if we have a very high content, or we can have just a part of the particle. We can cut these particles in several pieces, and one of the particles then we dissolve and measure that by ICP-MS. Or if we're lucky and we have nice gamma lines, then we can use one of the isotopes, measure a gamma emission spectra, which of course gives us the absolute information. Then we can do the calculus of the other isotope ratios. But for it alone, the CIMS and SNMS is very difficult to use as an absolute method.
Thanks. And do you have some experience with the cesium 137 and 135 ratio?
Yeah, in fact, we can do that. So there are different methods to do that. So first of all, cesium is a very volatile element. So if you heat your particle up by heating it with a red laser, for instance, the cesium is coming off. And then you can measure the isotope ratios in a very straightforward way. So that is easily done. But you always run the danger that you're probing only the surface of the particle, that you're depleting the cesium from the inside of the particle just by diffusion processes. So in a second way, you can do the same excitation scheme as I just showed you with the plutonium, that you have a selective isotope excitation scheme for your particles. And that can also be done. That is not the major focus of our work, but in collaboration with the Lawrence Livermore National Laboratory in the United States, we're doing exactly that. So it's very good at measuring these isotope ratios.
I know that there is a quite tedious work about the radiochemical separation of cesium from barium isotopes, isobar. And do you know if this technique can be more easy to separate, to recognize the different isobar, or is always needed a radiochemical separation?
With our technique, there is no radiochemical separation needed. So we can completely suppress the isobars by the laser excitation scheme.
Very interesting.
Other comments? I have maybe a silly question. The cross-contamination among the sample is a big problem in this kind of analysis or investigation?
So cross-contamination, or of course, so there are several possibilities. First, if you're looking at these tiny particles, you have to be very careful that these particles might not originate just from your lab. So that is something you have to make sure in the beginning. On the other side, if you have the particle itself there, then just a contamination on the surface doesn't really harm, because you can sputter off the surface, clean the surface by the ion beam, and start the measurement a little bit later when the surface is depleted of the first 2, 3, 4 layers. So everything you might deposit on the particle can be cleaned away.
I'm Gabriele Magugliani from Polimi. Thank you for the presentation. It was very interesting. I have just a curiosity, since I know practically nothing about the topic. In forensic, is there an interest in measuring ratios, isotopic ratios between different elements? Like, for example, uranium-238 with respect to plutonium-241, or the interest is mainly on single element isotope ratios?
No, in principle, you're also interested in the element ratios. And if you have the isotope ratios within one element, so plutonium 239, 240, 241, and on the other hand, you know the uranium plutonium ratio, then you can get all the information. And that was just two of many 4 isotope plots I could have shown. And many of these give you information, especially, as I pointed out, the abundance of plutonium-236 is a very important marker on the origin of the material. But that gives you what also Mario raised, that question. That gives you a high challenge to get reference material, because then you need to know how the ionization efficiency is, uranium versus plutonium, for instance.
Yeah, so the technique that you use is not suitable for this purpose.
I wouldn't say so, because if you cut that particle in different pieces and use one of the particles to dilution, measure the absolute uranium and plutonium contents with ICP-MS, you can get all the information. So by combining two methods, you can get your aim, but this method just alone is a bit challenging. So if you have exactly fitting reference materials, that might work out, but it's much more reliable to combine different methods for this case. It's like AMS. AMS also is not very often used as an absolute method, but only as a relative method.
Okay, and do these reference materials actually exist, or they have to be prepared in-house?
We found a way of producing this reference material when we do iron co-precipitation, and in the liquid containing the iron hydroxide, we have the uranium and plutonium, and then we do a scavenging. This is completely independent of the material, so all the elements are coming off at the same time. So there we can get a very good reference material, but that was only a first step. And as I mentioned, there's a European project just started that is called Metropoem, and this project just cares about how to produce these reference particles, liquid state as well as solid state.
Okay, thank you.
The last one by my side. And these very performant techniques have some particular range of masses where they are very performing, but or not, or in all the range of masses are performed.
In principle, you can use SNMS and CIMS from the very light one, from starting at lithium, all the way to the heaviest elements you can imagine. Of course, it is not suited for the noble gases because it's hard to get them in the solid state. So there might be an exception if you have like meteorites and inclusion of noble gases, or also fission product noble gases might be possible, but it is not the first choice. And if you have something that is only present in the liquid state, that is also not so good. But for all the other elements, it is pretty much suited. For the laser ionization, that is like 50% of the periodic system where it was demonstrated that you have excitation schemes working. And 25, 30 elements where you really did the combination and have it in a way of combining the resonance ionization and the CIMS. Maybe even less, maybe like 20, 25. But in principle, we are all the time working on extending that range and trying to measure new elements where we know that resonance ionization is working and combine that with our CIMS.
Thinking to the youngest that are connected now, which competencies they have to have in order to work in this field, so to perform this kind of analysis?
So what kind of background you need? Or?
Yes, competency, skills, but background, yes.
So most of the PhD students working on that machine are either physicists or chemists, and they have a very special background, I'd say, because they attended, of course, some lectures on radioecology, on radiation protection, on nuclear physics, to be a bit prepared, doing some hands-on training also. But there's no special like nuclear engineering course in Hannover, so all of them started either with physics or with chemistry.
Okay, so there is no a fixed, a specific course, but they have to acquire different competencies.
No, that's learning on this job.
Yes, yes, clear. Okay,
Good.
I would like to thank you very much for this very interesting presentation and discussion with a lot of questions. And also, of course, I would like to thank you all the persons that are connected. Thank you very much. And see you next time.
Yeah, it was my pleasure. Thanks for inviting me.